In this problem, they give us a graph of velocity versus time, and it's exponential, so v is directly proportional to t squared. But the question is asking about the net force. Well, how can we find the net force when they're giving us velocity and time? Well, we know that the derivative of velocity with respect to time is the acceleration. So the slope of the line here is our acceleration, and that slope is constantly increasing. So on a velocity time graph that's directly proportional to t squared, that would give us an acceleration graph with a constant slope. If the acceleration is constant, then the net force will be constant because F net equals ma. So the force would look the same as the acceleration graph, and the answer is E. In this question, we have two masses that are being dragged by a force and connected by a string with tension in the middle. And they want us to find out what that force of tension is. Well, the first thing we're going to do is solve for the acceleration of the system, and then solve for the force of tension acting on only block 1. So as a system, we would say F net equals ma. But in the system, that's 2 plus 1, so that's going to be 3a. So the acceleration dividing through by 3 is going to be F over 3. So now that we know the acceleration, all we have to do is apply this to block 1. So block 1 only has one force acting on it, the force of tension to the right. So we can say ma, in this case mass 1, times the acceleration is equal to the force of tension. We know the acceleration is F over 3, so the force of tension is F over 3, or choice E. In this problem, we have two forces that are acting on it, and they want us to figure out the force to put the piece of plywood into equilibrium. Now, we haven't learned about this yet, but in this particular situation, these forces would produce rotation, and we'll learn about that in a much later unit. But you can see that what we want to do is cancel out this 10 Newton force. Well, if we apply an additional 5 Newton force over here, that 5 newtons and 5 newtons will act the same as 10 newtons down. So the answer is A. In this question, they give us an equation for velocity as bt squared plus c, and b and c are constants. And the question is, what's the magnitude of the net force? Well, like the problem that we saw before, the net force is equal to ma, but they gave us a formula for velocity. How can we get velocity from, or how can we get acceleration from velocity? Well, we can take the first derivative. The first derivative of velocity with respect to time is the acceleration. So the power rule gives us 2bt. Throw that into F net equals ma, and we get m2bt1, which they just rearranged it. That would be 2mbt1, or choice E. In this problem, we have two blocks being pushed on by a single force. And the question that they're looking for is the force that the 2 kilogram block exerts on the 3 kilogram block. So we have this force that's acting on both, which we can look at as a system. And then we also have block 3 is pushing on the 2 kilogram block to the right. So therefore the 2 kilogram block pushes back on the 3 kilogram block. So to start this out, we'll do it as a system. So we say F net equals ma equals force of push. Our force of push is 20 newtons, and the system has a mass of 5 kilograms, so our acceleration is 4. Now, to find the block 3 on 2, what we're going to do is we're going to do the net force just on the second block. So that's going to give us a mass of 2 and an acceleration of 4, and that's going to give us the force of 3 on 2, which is 8 newtons to the right. But the question was, what's the force of 2 on 3? So that's not going to be 8 newtons to the right, it's going to be 8 newtons to the left. This question sounds very complicated, but in actuality it's quite simple. Basically, the Earth is exerting a force on a satellite, and the satellite exerts a force on the Earth. So for every force, there's an equal and opposite force. So the answer is C. The two forces are equal, and they're in the opposite direction, but it didn't ask that. Here we have an Atwood machine. So they talk about adding the masses, but in the end, we end up having 0.9 kilograms on the left and 0.6 kilograms on the right. And they ask us to find the acceleration. So I drew some free body diagrams here. For the block on the left, we have a tension up and the weight down. And I'm going to call down positive. That's the direction of acceleration. And we have an equal force of tension in the opposite direction of force of tension 1 and the weight of the other mass. So if we write a net force equation, we have F net equals ma. Then we have our force of gravity 1, positive, minus our force of tension 1, plus our force of tension 1, which will drop out to 0. They're equal and opposite forces, minus Fg2. So all we have to do is throw in the numbers. And because this was an AP question done before calculators, they asked you to use 10 instead of 9.8, and that gives you a nice 2 meters per second squared. This question is quite tricky. However, it's much better done with conservation of momentum, which we haven't learned about. But we can use forces to still figure out the answer to the question. So essentially you have a balloon, and the balloon has a mass m, and there's a smaller mass of a person that's hanging from the balloon that starts to climb the ladder. But the system starts with these forces in equilibrium. So the way that I like to think about this problem is just to say we have a tug-of-war. So the large person pulls on the rope, and the small person pulls on the rope, and the force of tensions have to be equal. They're equal and opposite forces. But when the person gets pulled on by this force, they have more mass, so they'll have less acceleration. So in this particular situation, we would have a large acceleration for this person and a small acceleration for the larger mass person. But that's not the end of the problem, because there is a force that is putting the system in equilibrium in the opposite direction. In the case of the balloon, it's the buoyant force, and in the case of the person, it's their weight. So instead of accelerating with different accelerations, they have different velocities, and those velocities are constant, and for the person, it must be a smaller velocity. So the answer is D. The balloon will move down with a speed less than v. I should have said larger v here. This will move in this direction with a smaller v. Here we have a block of 5 kilograms on an inclined plane, and they give us the sides 3 and 4, so we can use tan theta to get the angle. So the question is, what's the coefficient, the coefficient of the block is 0.3, and the question is, what's the magnitude of the force to drag the block up at a constant speed? So to do that, we want to have the net force be 0. So that means the force of the pull has to be canceled out by the force of friction and the force of gravity component, the Fg, in the x direction. So Ff plus Fgx are going to be canceled by Fp. So let's first find Fgx. That would be our opposite side of the triangle. So that's Fg sine theta. And we just throw in the numbers using 10 instead of 9.8 for the AP, and that gives us 30 newtons. For the force of friction, we need the force normal. And we know that the force normal is equal to Fgy. So that's going to be our adjacent side, so that's going to go with cosine. So the force normal, being equal to Fgy, is Fg cosine theta. So the force normal, throw the numbers in, comes out to 40. But we need to find out the actual value of friction. So using mu Fn, we can take this 40, put it in for the force normal, multiply it by 0.3, and that gives us a force of friction of 12 newtons. So write our equation, F net equals ma. It's not accelerating, it's moving at a constant velocity. So we have the force of pull minus the force of friction minus Fgx, and that gives us a value of 42 newtons, or choice B. In this one, we have an elevator, and the elevator is moving down, so it has a downward velocity, and it slows down to rest, which means we know that the upward force must be larger than the downward force. And they give us this upward force. It's 11,000 newtons. And they give us the mass of the elevator, so we can do mass times gravity, 1,000 times 10 instead of 9.8, and that gives us 10,000 newtons down. So the net force is going to be 10,000 minus 11,000, and it's a 1,000 kilogram massed elevator, so that just gives us an acceleration of -1. So if we look at this formula, we can just say that it descends 8 meters, its acceleration is -1, it comes to rest. They wanted to know what the initial velocity of the elevator is. So using Vf squared equals V naught squared plus 2a delta x, we throw in our numbers, and we get an initial velocity of 4 meters per second. In this problem, we have a block that has a force acting at an angle, this force of pull at angle phi. And it's across a rough surface, which tells us there is friction. And they tell us that friction is lowercase f. And they want to know what the acceleration of the block is. So all we have to do is find the horizontal component of F pull. So the horizontal component of F pull is going to be the adjacent side, or F cos phi. And then we can write our net force equation. So that's going to be ma equals, this is our force of pull to the right, minus the frictional force, and then all we have to do to solve for acceleration is divide through by m. The next question is a little bit more tricky. It says, what's the coefficient of friction between the block and the surface? So to be able to do this, we need to figure out what the force normal is. So to find the force normal, we can do a little free body diagram here and say that we have the weight down, there's a component of the force of pull up. That up is the opposite side, so that's F sine phi. And then we have force normal, which is acting up. So the force normal combined with F sine phi is going to cancel out mg. Or in our F net y equation, ma is 0. Then we have Fn plus F sine phi, so these are both up, minus mg. Rearranging, Fn is mg minus F sine phi. So now, since we have the force of friction formula and we have the force normal, we can just plug this in. So the force of friction becomes mu times mg minus F sine phi. Dividing through here to solve for mu, we get the frictional force divided by mg minus F sine phi. In this one, we have a block system, 3-block system, that's being dragged by a force F. And they want to know in which thread or which cord is the force of tension going to be the greatest. Well, if you think of it this way, this force of pull has to accelerate all 3 masses. So therefore, this force is going to be the largest. This is going to be the smallest because all it has to do is pull on 3m. This problem is so easy, it's almost difficult because it's so easy. So it says a block of mass 3 kilograms is at rest, and it's pulled along the surface by a force here. And the question is, what's the acceleration at 2 seconds? Well, all we have to do is go up to 2 seconds and see the force is 4 newtons at 2 seconds. So that's just F equals ma. So we know the force is 4 newtons at 3 kilograms, or 4 divided by 3. For this question, we have a block that's being pushed on by a force to the right that's holding up this block. Now, how is it holding up the block? Well, by pushing the block against the wall pushes against the block, creating a force normal. By having a force normal in place, now we have a force of friction acting up. So the force of friction acting up is what's creating the force that cancels out the force of gravity to keep it in place. So they want to know what's that value of mu. So if we draw a free body diagram, we can see that the force of push pushes against the wall, and that creates a normal force acting out. And that normal force acting out is equal to that force of push in. So in our F net equation, we can just do an F net y and say that the acceleration is 0 because it's not slipping up or down the wall, and that becomes FF minus FG, or FF minus mg. We can then add this to the other side and just say FF is mg. And we know FF is mu Fn, so solving for the force, we can just divide through and solve for F. So I made a mistake when I said solving for mu. We're solving for F in this case. But if you were solving for mu, you would just say mu equals mg over F. Either way, same math. In this question, we have a block on a ramp, and they're giving us a whole bunch of different forces here. N for normal force, lowercase f for friction, mg for the weight, and theta for the angle. So let's look at what the first question says. It says, which best represents the free body diagram for the box as it's accelerating up the ramp? Well, we know that if it's going to accelerate up the ramp, it needs to have a force that's parallel to the ramp and that's larger than the force of friction and the component of mg acting down the plane. So this is the right answer because FP is larger than friction plus the component of mg, which would be mg sine theta. The next question says, which figure represents the free body diagram if it is at rest on the ramp? So at rest on the ramp means that there has to be a force up the plane that's canceled out by a force down the plane. Well, in this one, we can see that we have our FGY and our FGX. Our FGX, this component, would be equal to the force of friction, so it could be at rest. Now keep in mind that if it's at rest, its acceleration is 0. But acceleration of 0 could be at rest, or it could be at a constant velocity. And that helps us with the last question, which says, what if it's sliding down the ramp at a constant speed? Well, the answer for this one is going to be exactly the same, because the net force is 0, so its acceleration is 0. It could be at a constant speed.